So just following up on alcohols, I wanted to point out that there's three types of alcohols. They can be classified as either primary, secondary, or tertiary. That's hard to say. And that's done according to how many R groups are bonded to the hydroxyl bonded carbon. All right. So if you take a look at the alcohol, this is the hydroxyl group. All right. And so this is the carbon that is bonded to the hydroxyl group. All right. So if that carbon there has only one other carbon bonded to it, it would be considered a primary alcohol. All right. Primary is often drawn like this with the one with the little degree symbol. An example of a primary alcohol would be 1-propanol. Ethanol would also be a primary alcohol. That's just, it would be missing this last carbon right here. So if you have a primary alcohol, the carbon that is attached to it would be considered the primary carbon. All right. And in fact, this term primary carbon is used even if we're not talking about alcohols. All right. If this was a bromide right here, instead of an OH, if this was a bromo right here, all right, we would say that this is a primary carbon that the bromine would be attached to, because that carbon would only be attached to one other carbon. All right. So an example of a secondary carbon would be this right here. This is by IUPAC naming, it's 2-propanol, but this is often called isopropanol. It's the same thing as rubbing alcohol. And if you take a look at the carbon that is attached to the hydroxyl, it has 2 carbons that are attached to it. All right, that makes it a secondary alcohol, and that makes that carbon right there a secondary carbon. All right, the last type of alcohol is a tertiary alcohol. The IUPAC name for this is 2-methyl-2-propanol, but it's more commonly referred to as simply tert-butanol or T-butanol. All right. The name that you should be responsible for would be this one right here, because that follows the IUPAC naming. All right. And again, secondary can be abbreviated like this, tertiary like this. But what makes this tertiary is that if you take a look at that carbon right there, there would be 1, 2, 3 different carbons bound to it. So that makes it tertiary. This next little part doesn't have directly to do with alcohols, but I figured it would be a good time to point this out, since we were talking about primary and secondary alcohols here. We can also describe amines as being primary, secondary, or tertiary. All right. So there is a difference, though. All right. When we were talking about alcohols, primary versus secondary was determined by the number of carbons attached to the carbon attached to the hydroxyl. All right. With primary amines, it's simply how many carbons are directly attached to the nitrogen. All right. So with an alcohol, there's only ever going to be one carbon attached to the hydroxyl. All right. But with amines, if you take a look at the NH, you can have one carbon attached. You can have 2 carbons attached to the nitrogen, or you could have 3 carbons directly attached, and that would be the difference between a primary, secondary, or tertiary amine. All right. So I want to point out this difference right here. If we named these amines the same way we do alcohols, you would consider this a secondary alcohol if this was an OH, because with alcohols it's determined by how many carbons are attached to the carbon attached to the hydroxyl. But with amines, what determines primary versus secondary is simply how many R groups are directly attached to that nitrogen. All right. So it takes a little getting used to, but once you practice it, it's pretty easy. All right. So moving into a little bit of chemistry. So these next 2 sections that we're going to be talking about here all have to do with oxidation state manipulation. All right. So what I mean by that is we learned in the last unit that we can take an alcohol, like there's a definition of oxidations and reductions that applies to organic molecules. All right. So for organic molecules, when you oxidize, it either involves the addition of an oxygen or the removal of hydrogens. All right. So in going from this alcohol to this aldehyde, we are essentially removing two hydrogens. Although this is line angle, remember that there's two hydrogens off this carbon right here, and there's a hydrogen there. So in going from this alcohol to this aldehyde, we have lost this hydrogen as well as one of the hydrogens here. All right, so because there's only one hydrogen left to that drawn to that carbon. All right, one thing I want to point out, even though with line angle drawings, normally we don't draw hydrogens that are directly attached to carbons, it's quite common, I would say more often than not, when you're drawing an aldehyde, that people go ahead and draw in that hydrogen, even though you might be thinking, okay, if I didn't show that part right there, you would assume that there's a hydrogen there. It's usually drawn anyways. All right. So in doing this, since we lose hydrogen, that's an oxidation, and in going from an aldehyde to a carboxylic acid, that is also an oxidation because we're gaining an oxygen atom. All right, so we can describe these three different points as different what are considered oxidation states. All right, this is the alcohol oxidation state, this is the aldehyde oxidation state, and this is the carboxylic acid oxidation state. All right, and so the way I'm organizing this is that the further this column right here would be the highest oxidation state, and this column over here would be the lowest oxidation state. And I'm going to kind of try to keep that consistent even when I'm down here. The stuff to the right is going to be highly oxidized. The stuff to the left is going to be more reduced. All right. So although there's several chemicals that can be used to oxidize, some of them, the one that the book tends to talk about a lot is this stuff called acidified potassium dichromate. All right. In reality, it's probably not as common as the IB curriculum would have you believe. There's a lot more common oxidation reagents out there. Sodium hypochlorite, bleach, is a very common oxidizing agent. Potassium permanganate is very commonly used. The thing is, as long as you memorize acidified potassium dichromate, which is drawn as Cr2O7 2- /H. So this means that H plus means there's some acid present, and this is the dichromate ion of that compound right there. Okay, so if you had a primary alcohol, all right, that would oxidize that primary alcohol to the aldehyde. So if you had enough of that material, though, it wouldn't just stop there. It would take that aldehyde and it would oxidize it one step further to the carboxylic acid. All right. So if you're careful about this, and you just add 1 mole of this for every 1 mole of this, you can get this to stop at the aldehyde. But if you add excess and you heat it up a little bit, you can get it to go all the way to the carboxylic acid. All right. Well, what if we had a secondary alcohol? All right. Well, we could take. The thing is, what's the oxidation state that would go up one step from the alcohol? All right. So if we remove a molecule of hydrogen from this, we would get a ketone. All right. So this acidified potassium dichromate will allow that reaction to happen. But as opposed to the aldehyde, where you could go one oxidation state further, we can't do that. We can't do that with the ketone. All right, this is kind of the end of the line as far as oxidation states are concerned. All right, so if we were to try oxidizing a tertiary alcohol, all right, well, notice that with the previous two examples, when we went from the alcohol to the aldehyde, we ended up losing a hydrogen from this carbon right here when we went to this step right here. Notice that there's 1 hydrogen that's attached right here, 2 hydrogens here, but there's only 1 hydrogen left in the product. All right. notice that there's one hydrogen right here, but now there's 0 hydrogens in the product. So in order to oxidize the alcohol, you need to have a hydrogen which is attached to that carbon right there. All right. Notice that with a tertiary alcohol, you don't have a hydrogen which is directly attached to that carbon. So that doesn't allow for this to be oxidized in the same way that these previous two examples could have. All right. So essentially that means that tertiary alcohols are going to be very stable against oxidation. That they don't like to get oxidized. There's not really something that you can make by oxidizing them. All right. So just like we can use oxidizing agents to go essentially up the oxidation ladder, all right, which would be going to things in this direction, there are some chemical reagents called reducing agents that will take things back down the oxidation ladder. All right, so we will go towards more reduced forms. All right, so the two common reducing agents are sodium borohydride, which is NaBH4, and lithium aluminum hydride, which is LiAlH4, and this is commonly referred to as LAH. Okay, so between these two reducing agents, sodium borohydride is generally considered to be a weaker reducing agent than lithium aluminum hydride. All right, so so starting here, notice I'm going to do this from right to left, and that's so that I can kind of keep the convention established, like more oxidized is over here. All right, so if you wanted to reduce a carboxylic acid, all right, sodium borohydride wouldn't work. It's too weak. All right, so the thing is, you're going to have to use lithium aluminum hydride. All right, so you might think, okay, well, that would reduce the carboxylic acid to the aldehyde. The reality is that the aldehyde, it's very difficult to get this reaction to stop at the aldehyde. If you take a carboxylic acid and you treat it with lithium aluminum hydride, you're probably only going to be able to fish out the alcohol at the end. All right. So even though this process proceeds through that aldehyde oxidation state, it generally is going to go all the way to the alcohol. All right. So by comparison, let's say that we did have an aldehyde. All right. Sorry. One last thing about this. Let's say that we did want to get the aldehyde. One way that chemists typically will do this is they'll, from a carboxylic acid, is they'll go ahead and say, well, let's just reduce it all the way down to the alcohol. And then once you have the alcohol, we can oxidize that back up one step to the aldehyde. All right, that's generally easier to do than trying to do this directly from the carboxylic acid. All right, even though it would be a two-step procedure. But let's say that we did have an aldehyde or a ketone. All right, even though we could reduce these down to the alcohols using lithium aluminum hydride, that would be a little bit like using a sledgehammer. This is a very powerful reducing agent, and generally in chemistry you want to try to use a reagent that is the mildest possible to get done what you need to get done. All right, so it's like why we don't use sledgehammers to tap in simple nails. All right, if you use the sledgehammer, it would tap in the nail, but it would probably also damage the wood. All right, so you use the tool that will get the job done while doing the least amount of damage to anything else that's around. All right,